All right, so right now you're going to take energy notes. And so the first thing that I want to have you guys do is instead of thinking about energy, think about time. And think about what you spend your time doing every day or on an average day. And when I have students do this in class, I give them a few minutes to draw. So go ahead and draw something that represents how you spend your day. Pause this video, draw it, and then resume. Okay, so now that you've drawn something to show how much of your day you do each of your activities, I'm going to show you what oftentimes a lot of students come up with. And if you have something completely different, that's completely fine. So oftentimes I'll see students draw a pie chart where they have things like they sleep for a certain amount of the day. So let's say they sleep this much. They watch TV. There's usually a big chunk of school, maybe some homework, and then maybe they eat, and maybe they also go to work. Okay. So this might be a typical day for a given student. Well, in a typical day, well, actually every day, whether you like it or not, is 24 hours long. And so if I take this and I decide that I do not want to do any homework today, okay, and let's say that I usually spend 2 hours doing homework here, and I don't want to do homework. So if I'm not going to do homework, then I'm going to have my day like this, and I'm just going to get rid of homework. Does that mean that I have 22 hours left in the day then? No, I do not now magically have 22 hours left in the day. In fact, I still have uh, this portion of my circle. I just am not going to spend it doing homework. Maybe I'll do it something where I'm wasting time. Let's say I wasted my time watching YouTube. Okay. So here I have my YouTube watching waste of time. It's not that the time went away. I've used it, lost it, although I did spend it. Like, it's just not productive anymore. And the same thing is true for energy. So I gotta move this out of my way. Energy cannot be created or destroyed. The other thing that you need to know is my favorite definition for energy. And my favorite definition for energy is that energy is the stuff that makes stuff do stuff. Now, we talked about this amount of time here where it was kind of like wasted time. Well, we have the same kind of thing in energy, and we actually call that dissipated energy. And I'm going to throw everything into this category that is just energy that's not particularly useful anymore. So one example of this would be that you just got to school, you realize your phone is dead, and so you hold your phone over the cars in the parking lot. You just walk around holding your phone because there's heat coming off the engines. And you're like, oh, good, there's some energy there. I'm going to collect it all and charge my phone. Well, that doesn't really work. So, yes, there is energy there, but it's not something that you can really get back. So dissipated energy is the energy you can't get back. For example, heat from a car, warmth from friction. So if you take your hands and you rub them really hard against each other, you'll notice that your hands get warm. That is a form of energy. It just, you're not really going to be able to do anything with that energy. So we're going to call it dissipated. Now I want you to think of all the other kinds of energy you can think of And I want you to write them down on your paper. Pause this video, and then once you've done that, resume. All right. Now we are going to talk about some of those kinds of energy. So the first one I'm going to talk about is kinetic energy. And kinetic energy is the energy that something has because it's moving. So kinetic energy is the energy something has because it is moving. So I want to have two examples here. One where if you are moving really fast, then I want to know how much kinetic energy you have. And if you're not moving, then how much kinetic energy do you have? Pause this, answer those questions, and then resume. Good. Okay, so if you are moving fast, that means you have lots of kinetic energy. And actually, the faster you go, the more kinetic energy you have. So you have lots. And if you're not moving, then you have zero kinetic energy. All right, the next one that I want to talk about is called chemical potential energy. So we are going to talk about three different kinds of potential energy. The first one I want to talk about is chemical. So chemical potential energy is the kind of energy that you're going to have if you have gasoline or diesel fuel. If you've taken biology, ATP is a form of energy. You could have um, batteries that have chemical potential energy in them. All of those would be good examples. So chemical potential energy is the energy stored in food, ATP, fuel, gas, diesel, batteries, people, nuclear, all that kind of stuff. Kind of throw it all in one pile of chemical. Now I want to do an example. So what you're going to want to do is leave between 12 and 14 lines, assuming you're using binder paper. Just leave them blank on your paper because we're going to do an example. We're going to come back and do another example of potential energy. Then we'll go back and do another example, and then we'll do another kind of potential energy, and then we'll do the third example. So our first example is a truck driving. And the first thing that you need to know here is what these arrows mean. So on all these drawings, you're going to see arrows, and the length of the arrow is going to represent how fast it's going. Now, what this means is that if it's going fast, so faster would mean longer arrow. And if it's not moving at all, I will have a dot. It'll just be a dot. Okay, so let's take a look at what we have going on here. So if I'm driving this truck from Atascadero through King City and ending up in San Francisco, I know that, first of all, I'm not going to get very far unless I have gas. So I definitely have chemical potential energy. The other thing I'm going to notice is that I'm moving. And if I remember from a minute ago, if I'm moving, that means that I have kinetic energy. So I'm going to do an energy pie chart for each of these. Okay, so now I have my 3 pie charts drawn. Now I just need to add what kind of energy I have. And just with time, I need to fill up my whole thing, and depending on how much I spend doing what in the day, this is going to be broken up into how much energy each of these things have. Well, at the beginning of my trip, because it's moving, I'm going to have kinetic energy. And let's say I have this much kinetic energy. I'm going to just write it as KE for kinetic energy. And then as I drive, you'll notice that the arrow stays the same length, which means that I'm going to have the same amount of kinetic energy for all three of these. Now that we have our kinetic energy drawn out for each of these and showing that the kinetic energy stays the same because my velocity stays the same, now I need to think about chemical potential energy because my car needs to use gas. So I'm going to label the first one with chemical energy. So my chemical potential energy should represent all the rest of this. All right, so now I have the rest filled in for chemical potential energy. But as you may know, by the time I get to King City, I'm not going to have as much chemical potential energy left anymore. I may only have this much chemical potential energy. And by the time I get to San Francisco, I'm going to have even less than that. So then the question is, what is this other wedge? That other wedge is going to be the energy that got, well, what you could say was lost, even though it's not actually lost. It's just in a form that's not useful anymore. You burn the gas, it's hot when it burns, the planet gets a little bit warmer. There's some friction between parts of the car. The car needs to push against the air and move it out of way. All of those things are going to use up some of your energy and put it in a form that is not useful to get that energy back out again. And so that is the energy we call dissipated energy. All right. So as you can see, my kinetic energy part of these pie charts is going to stay the same because I'm going to keep moving at the same speed. My chemical potential energy gets smaller each time because I'm using up some of the gas. And dissipated gets bigger and bigger because my chemical energy is essentially turning into this dissipated energy that is not going to be useful anymore. So now we're going to go back and we're going to talk about another kind of energy. But first, I'm going to introduce this. So this is going to be our next example. So with our next example, I want to notice that this is just a dot. And the dot represents something that is not moving. Okay, so not moving at the top. And if it's not moving at the top, I want you to pause this video and tell me how much kinetic energy does it have? Okay, so your kinetic energy should be 0 because it's not moving. But at the bottom here, you can assume that it is at a height of 0.0000000000001. In other words, basically a height of 0, but it's barely not on the ground yet, which means it's still moving, but at a height of 0, and you'll see why that's important later on. So this arrow is much bigger, which means it's going much faster. What does that mean for our kinetic energy? Good. So this is moving faster, which means that my kinetic energy is big. And in the middle, you'll notice that my middle arrow is somewhere in the middle. So it's going, so it is moving, but it's not going super fast or super slow. It's somewhere in the middle. So I'm going to call it kinetic energy is medium big. Beautiful. So if I'm dropping this thing, I need to figure out what other kind of energy I have. Well, the other energy that I have is something from it falling and being held up high in the first place, and that is called gravitational potential energy. So we're going to go back up to the notes part, and I'm going to do gravitational potential energy in green. And gravitational potential energy is the energy that something has because of how high up it is. So the farther up it is, the bigger my gravitational potential energy would be. And if I'm all the way on the ground and I have nowhere left to fall, then I would say that my gravitational potential energy is zero. All right, so gravitational potential energy is the energy something has because of how high it is. So how high off the ground it is. If you are up really high, then you have lots of gravitational potential energy. And if you're on the ground or really close to the ground, then your height is zero and your gravitational potential energy is also going to be zero. So let's look at the example. So up here at the top, this is really high up, which means that I'm going to have a big gravitational potential energy. And in the middle, I'm at a medium height. So medium height would mean that I have a medium amount of gravitational potential energy. And at the bottom, my height is zero, which means that my gravitational potential energy is also going to be zero. So let's talk about what this looks like in terms of your pie charts. So I want you to pause this and I want you to try to make your pie charts and then resume. All right, so now let's do it together. So my kinetic energy at the very top is zero. So I'm not going to have any part of this be kinetic energy, but it does have a lot of gravitational potential energy. So all of this is going to be gravitational potential energy. At the bottom, I have the opposite thing happen. My gravitational potential energy is going to be equal to zero because it's basically all the way at the ground. But now my kinetic energy is going to be really big because it's moving fast. In the middle, and you could divide it however you like, but I noticed that this thing was a little bit more than halfway up. So I'm going to say that there's a little more than half gravitational potential energy, and the rest is kinetic. So what you'll notice is that as I get farther up, I have more and more gravitational potential energy because it's farther up in the air. And the farther down I get, it moves faster and faster, causing there to be a bigger and bigger kinetic energy, or the red wedge of this pie chart. So now I need to talk about this in terms of conservation of energy. So when we talk about conservation of energy, we know that the amount of energy needs to stay the same. Well, in this case, we have all gravitational potential energy at the top. So if I had a total of 300 of joules of energy in my system, then I need to have 300 joules of gravitational potential energy because there's nothing else there. And at the bottom, all my energy is kinetic energy. So if the entire thing is 300 joules of energy here, then I know that my kinetic energy needs to be equal to 300 joules. By the way, joules are the unit for energy. And in the middle, since I have both gravitational potential energy and kinetic energy, the total still needs to be 300. So what I need to do is just add the two together. So my gravitational potential energy plus my kinetic energy is going to be equal to 300 joules. All right, so the next one. In this next example, we have a piece of who knows what. I usually have students decide what it is. Let's say it's Kentucky Fried Chicken. Okay, so we have a piece of fried chicken, and what we're going to do is we're going to take a spring, kind of like the one inside your pen, and squish it down, and we're going to let it go. And when we let it go, we are going to have a piece of Kentucky Fried Chicken go flying into the air. So we need to talk about the energy in a spring. And conveniently enough, I'm going to call that spring potential energy. So we're going to go back up here. We're going to do the notes again. And this time I'm going to do spring potential energy. All right. So spring potential energy is the energy stored in a spring when it is either stretched or squished or bent. So when I say the energy stored in a spring because it is stretched or squished, I could also be talking about something that's elastic, like a rubber band. Or I could bend a spoon and essentially store some energy in the spoon. And then when I let it go, it goes flinging whatever food I have in the spoon off into space. So, plastic spoon. A, a bouncy ball is kind of rubbery. You can squish that. And when it hits on the floor, it gets squished a little bit and then it'll bounce back up as it comes back, just like a spring. So, it could also be a bouncy ball. All right, so if a spring is not squished, then there is no spring potential energy in it. So if you just have a spring sitting there, regardless of if it looks extended or squished, as long as it's sitting there and nothing's pushing or pulling on it, then your spring potential energy is zero. All right, so we have the spring potential energy is the energy stored in a spring or rubber band or plastic spoon or bouncy ball because it is stretched or squished, I should say, or bent. If a spring is not stretched or squished, then your spring potential energy is zero. So spring potential energy, I'm using as SPE. My gravitational potential energy is GPE. My chemical potential energy is just CE. And my kinetic energy is KE. Now, if you are in AP physics, then kinetic energy is going to just be K. Chemical potential energy we never talk about. Gravitational potential energy in AP physics is UG. And for spring potential energy, that is going to be US. All right, now take a look at this example. Here for the first one, in the first here, this spring is compressed. In these three, the spring is not being stretched or squished. That's just the natural length of the spring. I want you to draw an energy pie chart for each of these four situations. Pause the video, do it, and then resume, and I'll go over it. All right, so the first thing that I want to do is I want to identify what kind of energy I have in each of these four situations. So my spring potential energy here at the beginning is big because my spring is squished. For these three, my spring potential energy is zero because my spring is not being squished or stretched. That's just the natural length of the spring. The second thing I want to do is look at my kinetic energy. And my kinetic energy is going to be big if I'm going fast and small if I'm not. All right, so now I'm going to think about kinetic energy, and kinetic energy is related to how fast things are going. So for position 1 and 4, you'll notice that it's not moving. So at those points, because it's not moving, my kinetic energy is zero. For position number 2, I'm going really fast, which means I have a big kinetic energy. And kinetic energy for number 3, I'm going slower, so that means I'm going to have a small kinetic energy. Then the last thing I need to think about is my gravitational potential energy. So my gravitational potential energy for each of these. All right, so remember that gravitational potential energy is related to height. So some students will tell me that number 1 is at a height of 0. To show you something, I'm going to assume it has a very small height, which means that I have a very small gravitational potential energy. And up here at number 4, I have a big height, which means I have a big gravitational potential energy. And in the middle, too, I have a small one and then a medium size. So every time my gravitational potential energy then is going to get bigger because my height is getting bigger. All right, so let's do pie charts. So when I start to draw these, I'm going to start with my gravitational potential energies because I want to make sure that I start very small and I end all the way big. So I'm going to start here with just a small gravitational potential energy. And then the next one needs to be bigger because my Kentucky Fried Chicken is just a little bit higher. So let's say it has this much gravitational potential energy. The next time it's quite a bit higher up. And for the last one, it's all the way up in the air. And there is no other kinds of energy, so that means I know that it must all be gravitational potential energy. All right, so now that I have my gravitational potential energies colored in, it makes it a little bit easier for you to see how the gravitational potential energy is getting bigger and bigger as we go along. Now, I'm going to go back to the first one again, to Kentucky Fried Chicken number 1, when the spring is all the way compressed. And although I have a very small gravitational potential energy, you'll notice that I have a very big spring potential energy. So I'm going to go ahead and label that spring potential energy. All right. So then for number 2 and for number 3, I notice that I have a big kinetic energy and a small kinetic energy. And I have no spring potential energy for 2, 3, or 4 because the spring is not being compressed at all. So this is just kinetic energy here, and this is also kinetic energy. All right, so there we go. We have everything done. So you'll notice I only have spring potential energy at the very beginning when the spring is compressed. My gravitational potential energy gets bigger and bigger as the blob gets farther up in the air. And my kinetic energy is small when, well, is so small that it's 0 when it's not moving and is really big when it's going fast, which happens to be when it's close to the ground. Let me know if you have any questions.